All right, now let's look at the second page of that section of that sheet on overview of solving algebraically. Wanted to just remind you about a couple special cases. So let's look at the system in number 4. On this one, do you see how the x and the y's, they're on the same side of the equation and really already in the same order? This one would probably be best done using addition. Okay, just because of how it looks. Looking at it, I'm thinking about trying to get rid of those x's, and I noticed that I have a 5 and a 10. So really, I could just multiply the second equation by 2 to make a 10 happen, but I really want a negative 10, so I'm going to use a negative on that. So the first equation could just stay as is, and then with the second equation, I'm going to multiply through by negative 2. And when I do, I've got it so that the x's cancel out. But the y's also cancel out. So on that left side of the equal sign, I have 0, where on the right side, I have negative 21. There's no x equals or y equals, so this is one of those special cases. So remember how there's really 3 ways lines could look. They could be intersecting, parallel, or they might be the same line really. When this happens and you get something like 0 equal negative 21, some false statement, but no x, no y, but then a statement that's false, that tells you you have no solution. Okay, really the lines would have been parallel. Okay, if I if I did look at what these lines would look like if I solved them for y and graphed them, they would look like parallel lines. Okay. All right, now on this one, the y is by itself already, so I'd probably just go ahead and use substitution, even though I got that fraction. So I'm going to circle the y in the top equation, and then what I'm going to do is take that 1/2 x minus 3 and plug it in for that y. So I'm going to take the 3x minus 6, but right there where the y used to be, I'm going to be putting the 1/2 x minus 3. All right. Now I'm going to distribute the 6. So I'm working now on just solving this equation. So I'm distributing the 6. So I get minus 3x plus 18 equals 18. So the 3x take away 3x, those would add up to be 0. They would cancel out. And I'd be left with a true statement, 18 equal 18. But we know it's a special case because we don't have an x or a y. So this is true, and you would have infinitely many solutions. And they would be all the points on the line. Okay, when you do the problems that have the special cases in them, they sometimes give you 2 problems to do within the one problem. They might both be no solution. They might both be infinitely many, or you might have one that works and one that doesn't. Okay. And so you'll have these bubbles that you choose. So for this one, you would bubble in no solution. For this, you would bubble in infinitely many, but it's not infinitely many points anywhere. It would be just infinitely many solutions that are the points on the line. So this one usually has this extra little thing where it gives you the set braces. And you say it's the set of all ordered pairs such that they fall on this line. So really, both of those equations would turn out to be the same line if I had solved that first one. And sometimes they'll ask for this second part, and they set it all up, and right there they want you to put what you would get if you had rearranged the equation so it was y equals. What you would put there would be the rest of the equation. Okay? So these are the two special cases. This question number 5, turned out we used substitution since we already had the y equals. We already had one of the variables by itself. Okay, doesn't really matter how you solve it, but you need to get straight that with this special case, you're going to get something like 0 equaled negative 21. You're going to get something where the two sides are not equal. With this special case, you're going to wind up getting things like 18 equals 18, some kind of true statement. And then with this case, the usual case, that's the one where you'll get either an x equals or a y equals, like the variables don't cancel out. It's not a special case. These are the special cases. These are the special cases, okay? All right. So really when that happens, it's no solution because really the lines were parallel. You just didn't know it ahead of time. And really the best thing to do is just to try to solve algebraically and just see if you get a false statement or if you get a true statement. What's really going on this one, on the right, if you get infinitely many solutions like that, what was really going on there is the lines were the same, really. They were coinciding lines. So every ordered pair on the line was common to both. Okay. All right, now just kind of summarizing what your plan should be. So we know that the lines could intersect. Most of the time we just assume that, and what we're doing is looking for that point of intersection, and that ordered pair would be your solution. The lines might be parallel. If they do, they have no point of intersection, so there's no solution. If they intersect, okay, then you're going to have the solution would be the ordered pair where they intersect. All right, now what happens when you solve algebraically on that second case is you're going to get something false, like 0 equals negative 3 or 12 equals 6. That's going to be the no solution case. The lines were parallel. Now, on the third one, you have maybe two lines, two equations to start with, but they actually are the same line. If you were to graph them, they'd be the same line. So you have infinitely many solutions. So if the lines are the same, then you have infinitely many solutions. And what will happen algebraically is you'll get something like 0 equals 0 or 12 equals 12 if you tried to solve algebraically. Okay. All right, now down here, just a little more on your plan. All right, so if one of the equations has a variable by itself, like x is already by itself there, or on this one we could go either way with it, like we know y equals 5x minus 2, then we would use substitution on these. Okay. If both equations are in the form ax plus by equals c, where the x and the y are on the same side like that, okay, and the numbers out in front of x and y are not just a 1 or a negative 1 like here, then addition method works best. Okay, so substitution works best if one of the variables is already by itself. The addition method works best if none of the numbers out in front of x or y are a 1 or a negative 1. And then on the last one, an example of that would be if you had like 3x plus y equals 7, and then maybe 2x minus 4y equals 15, then you could use either substitution or addition. The key is that if there's a 1 or a negative 1 in front of one of the variables, then that means you could get it by itself without creating fractions. And so substitution would work okay, but you also could pick a variable to eliminate and that would work well also, okay?